We have reached a remarkable point in human history. At this very moment, wheeled machines made of metal are moving across the reddish dust of Mars. A spacecraft built here on Earth was intentionally consumed by the storm clouds of Saturn. Cameras created by human beings recorded Pluto's frozen landscapes from a distance of less than 13,000 kilometers after traveling through empty space for more than 9 years. From the outside, all of this makes it seem as though we have finally learned how to handle space. Crossing the darkness between worlds can look almost routine, no more extraordinary than taking an airplane from one city to another. That impression is reassuring, but it is also misleading. We can travel through the solar system with surprising efficiency in one direction. In another direction, we run into a barrier so severe that it changes the entire problem. There is a route that should be the simplest and least expensive in theory. It leads toward a region that is, in a very real sense, close at hand. Yet this destination remains one of the most difficult challenges that engineers have ever confronted. The route I mean is upward, leaving the broad, flat surface in which the planets orbit and approaching the sun from above or below, rather than viewing it from the side as we almost always do. This means entering the vertical axis of the solar system over its northern or southern face. At first, the idea sounds almost laughably straightforward. If the solar system is like a rotating plate and you want to get away from that plate, why not simply point a rocket upward and ignite the engines? This is where the universe delivers an unpleasant surprise. The laws of physics do not merely make the journey inconvenient, they place an enormous obstacle directly in its path. The reason is that escaping upward costs almost 10 times more energy than reaching Pluto. We have not properly photographed the region in question, and what lies there is still largely unknown. Engineers have also had to devise a remarkable maneuver to get through the barrier. In order to climb away from the planetary plane, a spacecraft must first dive almost directly toward the sun. Before we go any further, there is an uncomfortable fact about your own movement that has to be understood. Even if you are sitting perfectly still, without moving a muscle, you are traveling at an extraordinary speed. Earth is not stationary in space. It sweeps around the sun at approximately 30 kilometers per second. In terms that are easier to picture, that is more than 100,000 kilometers per hour. Here is the detail that changes the entire calculation. Every rocket launched from Earth, whether it rises from Florida, from the launch facilities of Kazakhstan, or from anywhere else on the planet, begins its journey with that sideways motion already included. The vehicle leaves the launch pad carrying Earth's roughly 30 kilometers per second of orbital velocity. That speed pushes it laterally around the sun. For most missions, this inherited motion is an enormous advantage. When a spacecraft is sent toward Mars or Jupiter, Earth's sideways velocity performs much of the work automatically. Think of stepping off a spinning carousel. You are not beginning from rest. The rotation has already given you a strong outward motion. The spacecraft needs only a relatively small additional push in the appropriate direction. With a few extra kilometers per second, it can be placed on a path toward another planet. Now imagine the entire solar system as a huge vinyl record turning beneath you. The planets are like tiny ants moving across its surface. Traveling from one planet to another is similar to an ant walking toward the rim. It is difficult, but it follows the natural direction of the rotating surface. Trying to move straight upward is completely different. To leave the planetary plane permanently, at a right angle to the orbits and to the motion shared by nearly everything around you, the spacecraft must first get rid of the 30 kilometers per second it already possesses. It has to spend an enormous amount of fuel simply canceling its horizontal motion relative to the sun. Only after that can it begin gaining altitude along the vertical axis. Engineers describe this requirement with a quantity called delta V. It is a measure of how much total change in velocity a maneuver requires. Compare the two routes. Leaving Earth's orbit and heading toward Mars requires roughly 4 kilometers per second of additional delta V. A spacecraft aimed directly out of the solar system's flat disk needs close to 30 kilometers per second. That is nearly 8 times as much change in velocity for a journey that looks much shorter when drawn on a map. Earth's motion gives us what amounts to a free pass for traveling across the disk in many directions. But the same motion becomes a nearly impassable wall as soon as we try to rise out of the disk. That is why a strange comparison is possible. Reaching a location only a few million kilometers above one of the sun's poles can require far more energy than crossing the billions of kilometers between Earth and Pluto. Because this vertical escape is so costly, almost no spacecraft in human history has seriously attempted it. The result is an almost embarrassing fact. In the year 2026, the regions directly above and below the sun remain among the least explored places in our entire planetary neighborhood. Consider how extreme that contrast is. We possess maps of Mars detailed enough to let mission planners select a particular crater for landing. We have examined the volcanoes and concealed oceans associated with the moons of Jupiter. We have photographed rings, comets, and asteroids as large as stadiums. Yet the polar regions of our own star, the star whose warmth reaches your face and makes life on Earth possible, have barely been observed directly. This is not simply a matter of scientific pride. It is also a question of safety. The sun's polar regions are connected to some of the most violent behavior produced by the star. That is where the fastest and most powerful solar wind emerges. It is also where the sun's magnetic field undergoes its great reversal, turning itself upside down approximately every 11 years and completely exchanging the positions of its poles. The consequences of that process reach all the way down to our daily lives. Solar activity can disrupt satellites and interfere with radio communication. It can even affect the stability of electrical power grids on Earth. Yet, for all these years, we have watched the sun almost entirely from the side, circling around its equatorial region and looking toward its waist. It is like trying to understand the weather on an entire planet while standing only along its equator, without ever seeing what happens near the frozen poles. We like to think that we know our star, but our view has almost always come from the easiest angle available. Across the full history of space exploration, only 2 missions have obtained anything resembling a privileged view of the solar poles. 2 missions despite decades of launches and attempts. The first was Ulysses, launched in 1990 through a collaboration between American and European space agencies. To escape the tyranny of the planetary plane, it used an ingenious and somewhat counterintuitive strategy. Rather than trying to climb directly by brute force, the spacecraft traveled all the way to Jupiter. There, it used the giant planet's immense gravity as a slingshot. Jupiter redirected the probe and threw it out of the solar system's flat disk at a steep angle. The method was clever, and Ulysses returned valuable information. But the mission had a major limitation. Its technology came from the 1980s, and it did not carry cameras capable of producing actual portraits of the solar poles. It could sense its environment, recording particles and magnetic fields, but it could not show us what those regions looked like. In a sense, it was like trying to understand a dark room by reaching out with your hands while having no way to see inside it. The second witness is operating now. The mission is called Solar Orbiter, and it launched in 2020. Instead of receiving one dramatic gravitational kick, Solar Orbiter has been using repeated encounters with Venus to tilt its orbit a little more each time. Pass after pass, the spacecraft has patiently increased its angle above the usual plane of the planets. Then, in March of 2025, an event occurred that is likely to become part of the history books. Solar Orbiter sent back the first direct images of the sun's south pole. The view on the screen was not peaceful or neatly organized. What appeared there was a scene of intense magnetic disorder, with the field lines tangled, twisted, and scrambled. It was a landscape almost unrelated to the orderly surface we had always watched from the side. The observation confirmed a deeply unsettling suspicion. The regions above and below the sun may be entirely different worlds from the one we thought we understood. We have only begun to work out what is happening there. The sun is not the only part of our neighborhood hiding its shape along the vertical axis. There is an even larger uncertainty surrounding the structure that contains everything we call home. The sun is constantly releasing a stream of electrically charged particles. This solar wind flows outward in every direction, expanding until it forms a vast protective bubble around the entire solar system. That bubble is called the heliosphere. Earth and the other planets travel inside it, and its presence matters enormously. The heliosphere acts as a shield, deflecting or weakening much of the dangerous cosmic radiation moving through the galaxy. For decades, the standard picture in textbooks gave this bubble a graceful, comet-like form. It was imagined to have a rounded front facing the direction in which the sun moves through the Milky Way, followed by a long, stretched tail extending far behind it. The idea was reasonable, and it even had a certain elegance. But around the year 2020, scientists examining measurements from American space missions began to favor a very different possibility. Their models suggested that the heliosphere might not resemble a comet at all. Instead, it could look more like a crushed croissant, an uneven structure with two relatively short arms and no immense tail like the one shown in older illustrations. Why is there still no final answer? The obstacle is the same one that has limited our understanding from the beginning. No spacecraft has traveled far enough above or below the solar system to leave the heliosphere and photograph its overall shape from the outside. The famous Voyager probes did pass through the boundary of the bubble, but they exited through its outer regions. They did not climb high enough to look down on the heliosphere from above. Trying to determine its true outline from those measurements is like attempting to map an entire house while looking through a single keyhole in the front door. Until a spacecraft can rise far away from the structure and view it from a new angle, we will remain inside the bubble, gathering clues without seeing its complete form. That raises the practical question: how could a mission ever reach such a position? A rocket cannot simply carry an unlimited supply of fuel, and Earth gives every departing spacecraft a sideways speed of roughly 30 kilometers per second. That existing motion is one of the greatest barriers to traveling out of the familiar plane of the planets. Trajectory specialists have proposed an answer that sounds almost backward. It depends on a maneuver known as the Oberth effect, and it requires a spacecraft to do the opposite of what instinct suggests. Instead of aiming directly upward and trying to fight its way against the sun's gravity, the probe would first be sent inward, toward the sun. It would be allowed to fall deeper into the star's gravitational well. As it descends, gravity accelerates the spacecraft to an extraordinary velocity. At its closest point to the sun, the probe could be moving at hundreds of kilometers per second. That is the crucial moment, when the spacecraft is already traveling at its greatest speed and gravity has supplied much of the energy. Its engines would fire. The principle behind this maneuver was developed by the pioneering rocket theorist Hermann Oberth as far back as 1929. A rocket engine can produce a much greater change in a spacecraft's orbit when it burns while the craft is moving extremely fast inside a powerful gravitational field. The same propellant can deliver a far larger result under those conditions. The easiest comparison is a swing. A push delivered at the lowest point of the arc can have a much greater effect than the same push applied elsewhere. At perihelion, an engine burn uses the spacecraft's enormous existing speed to amplify the boost. With the engines firing at exactly that point, the probe could gain enough energy to cancel much of its sideways motion and redirect itself toward the vertical axis. In that sense, the plunge into the solar furnace would become the launch ramp for the climb toward the top of the solar system. The most dangerous part of the journey would also provide the leverage needed to escape the plane in which the planets orbit. A second technology could make the maneuver more practical: the solar sail. Imagine a huge sheet of highly reflective material, perhaps several kilometers across, deployed in space. It would not need to burn fuel to produce thrust. Instead, it would respond to the faint but continuous pressure of sunlight striking its surface. That pressure is gentle, so a solar sail would not transform an orbit quickly. It might take years to gradually tilt a spacecraft's path by the required amount. Yet sunlight never runs out in the same way chemical propellant does, and the sail can continue working without an engine burn. Its force is small, but it is persistent. Many engineers therefore see the two methods as complementary. A solar sail could slowly shift the spacecraft's orbit and bring it closer to the desired trajectory. Once the probe had reached the right region, an Oberth-style dive toward the sun could provide the final, powerful change in direction. Together, patient orbital adjustment and a high-speed solar maneuver might finally make travel along the vertical axis possible. If such a mission were ever completed, what would the spacecraft discover from that distant vantage point? The first surprise might be how much cleaner the surrounding space appears. The plane occupied by Earth is not perfectly empty. Across billions of years, collisions between comets and asteroids have produced fine debris, leaving a thin veil of dust spread throughout the planetary disk. That dust is visible from Earth under the right conditions. On a very dark night, sunlight scattered from the particles creates a faint, diffuse glow called zodiacal light. It is a subtle reminder that the region around the planets contains far more material than the darkness of space seems to reveal. A probe traveling straight above the planetary plane would leave much of that haze behind within only a few months. From higher up, the view would be clearer and more sharply defined. Such an environment could be especially valuable for telescopes searching for evidence of life around distant stars. Observatories positioned away from the dust of our own solar system would have a cleaner view of the universe beyond it. The second revelation would concern the Sun itself. From the side, especially near the equatorial region, the star appears dominated by turbulent and constantly shifting plasma. A probe traveling above the poles would encounter something different, a cleaner, faster stream of solar wind flowing outward from the polar regions. That perspective would allow scientists to study the Sun in a setting where its outflow is less obscured by the complex activity around its middle. The spacecraft would not simply be looking at the star's familiar face, it would be observing the way the star releases its influence directly into the space above and below it. Then there would be the image scientists have never been able to capture, a view of the complete solar system from above. From that position, the planetary system could appear as a broad, organized disk. The rings of dust would stand out across the surrounding darkness. The planet's orbital paths would form a series of concentric circles, revealing the geometry that is difficult to appreciate from within the plane itself. Beyond those orbits, the view could also include the actual outline of the heliosphere, surrounding the solar system like an enormous, irregular boundary. For the first time, we might see whether its shape truly resembles a comet, a flattened crescent, or something more complicated than either comparison suggests. That portrait is still absent from humanity's collection of space images. We have seen Earth hanging alone against the blackness. We have photographed the far side of the moon. We have looked back at our planet from great distances and watched the familiar worlds of the solar system appear as points of light. Yet no spacecraft has ever shown us our entire planetary home from above. Reaching the regions above and below the solar system would therefore change more than the angle of a photograph. It would expand the way we think about exploration itself. At present, nearly all of our experience is confined to the flat disk where the planets travel. We have learned to move across that disk, but we have barely begun to navigate around it. A successful mission along the vertical axis would give us a genuinely three-dimensional map of our cosmic surroundings. It would reveal the solar system as a structure with height, depth, boundaries, and changing layers of dust and plasma. The route could depend on the slow persistence of a solar sail, the extreme velocity of a dive toward the Sun, or a combination of both. Each method offers a very different way to reach the same unexplored direction.